Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Jairo Armijos-Abendaño with us today.
Hello, everybody.
Hi,
Thank
Jairo.
you. Hey,
Where
hello.
are you at? What's your geolocation?
I am in Quito, in Ecuador. We are near the equator. So here now we have a wonderful weather. It's very around 25 degrees. So it's really nice.
See. Yeah, you have the honor of being the very first person from Ecuador to do one of these. So that's awesome. That's awesome.
Oh, great, great. I am really happy to be here to talk about a little bit about Ecuador, about my work.
Yeah, great. Well, you can certainly talk about Ecuador. I'm all ears. That's fantastic. So speaking of that, Jairo, what do you like to do for research?
Yes, I am very interested in investigating molecular tracers.
Okay.
I have been doing that over 6-7 years already using telescopes are in different countries. For example, in Spain, I have used telescope in States, and also the Opera telescope, which is in Australia. I have been using this to observe molecular traits that are actually very important to study the chemistry and the heating mechanism in the interstellar medium. That is I will say, my main research, my main interest in astronomy.
Cool. Are you doing, so these days in 2020, 2021, are you doing your observing remotely, or is there issues with traveling these from the pandemic?
Yes, we were doing observation actually this year with the IRAM telescope in Spain. We observed remotely, but before, 2 years ago, actually it was really great that I was in Spain, in the south, observing with the IRAM telescope 3 times. So that was really good. But yes, now it's really nice that we can we can observe remotely.
Good. Well, hopefully in the near future, you'll get to go visit Spain and do it in person again. And that is going to bring us to this really lovely APJ article on the effects of UV photons, X-rays on the chemistry of the SGR B2 cloud, Sagittarius B2 cloud. And Jairo, take us away.
Yes. In this paper, we focus on the study of, as I said, molecular tracers. I mean, 3 tracers, each CO plus, each CO, and CO plus, which are good tracers of photo-dissociating regions and X-ray dominated regions. So these are good tracers. So we observe these molecules, different lines of these molecules with different telescopes. So we observe these to study selected regions that we know in advance that are affected by different heating mechanisms. We observe, we carry out this observation in the galactic center, in the Sagittarius B2 cloud. So that is a really nice cloud in the galactic center in the Milky Way, where we have a lot of things happening. We have star formation there. We have regions that are affected by X-rays, and we have also regions that are quiescent. So it's a really nice target to study. In addition, the galactic center in the Milky Way is the closest nuclei that we have. So that is another reason to study this region.
Okay. Very
Yes.
nice.
So we complement our study using X-ray data, which is archive data observed with the XMM Newton telescope. So we use this data to complement our radio study. What was actually really nice, because we learn a lot about what is going on there. I mean, what is happening when we study, when we investigate this region using X-rays. So that was really nice. So I'm going to talk about this in detail later.
Okay, great.
So what we carry out this study, we are very interested, as I said, in investigating molecular traits that can be used to disentangle the effects of X-rays and UV photons in the ISM. So we carry out this study in the Galactic Center, but after that, when we will know more about this, we will use tracers to study the nuclei of other galaxies. So this is the main reason of this study. So if please we go to figure 1.
Figure 1.
Yes.
Yes, there we go.
Figure
1, and there we go. See if I can blow that up a little bit. Yes, there we go. Figure 1.
Yes, as I said, observe with the IRAM telescope in 24 Photons in the Sagittarius B2 region. Okay, these positions are shown in this figure on the top panel. Yes, with white circles. We have here the 15 positions that we observe with the IRAM telescope, 50-meter telescope. So the figure that we have in color is the radio continuum emission, which is really good to know where we have a star formation and where we have a UV radiation. So we use this map to select several positions in Sagittarius B2. For example, position 1 and 2 are really good targets of regions affected by UV photons. Over there, we have Sagittarius B2N, Sagittarius B2M, which are really nice targets where we have star formation, a lot of star formation there. So we choose these regions and others also that are good targets to study the effects of UV radiation.
Okay.
On the middle panel, we have in colors, we have the X-rays in 24, and on the bottom we have X-rays, but in 2012. Yes, we have two epochs over there. As you can see here, we have the X-ray emission in this region has changed.
Yeah,
has changed
quite a bit.
Yes, yes, that is actually really nice because, excuse me, really nice because people think that this variability in the X-rays is due to the stars that originate in Sagittarius A star, the supermassive black hole in the Milky Way. So people think that the reason of this variability is the flares that are produced in Sagittarius A star. So what we are seeing here is that the clouds in the galactic center show something like an echo that is happening there, over there. So for this reason, we use this data to study how X-rays affect the regions that we are studying here. As you can see here in the X-ray map of 24, we have a lot intense X-ray emission over there. For example, in position 1, 2, 6,
Yeah.
we should detect the effects of the X-rays. But on the other hand, in 2012, the emission has changed, and actually it has moved to the south part of the map. So
Yeah.
that was really interesting. So we observe, and then we use the radio emission and X-rays to study these effects. So please, we have over there 13 positions. If we move to the next figure, please.
Okay.
So we observe, as I said, 3 molecules, HOC plus, HCO, and CO plus. These were the main tracers. We also use CO because it's actually this molecule is really important to derive the abundances. So we observe as well this molecule. And here in figure 2, I am showing the emission of each CO and also the emission of other molecule, each 13 CO plus. As we can see here, the emission of the each 13 CO plus is more extended, yes, than the emission of each CO 1 to 0, yes.
Yeah.
But the reason of that is because, yes, is because each CO is not so abundant in this region. So we are detecting only the emission coming from the central region where we have the densest regions in the cloud. So that is the reason of that. But was really nice to see how the emission is there. In here in this figure, we also have the positions that we observe with the IRAM telescope, with the radio telescope. And on the next figure 3, what we have in the X, we have the positions, or 13 positions, and the Y axis we have the flags of the iron line. We have the iron line at 6.4 Kep. Yes, these fluxes were obtained using spectra observed with the XMM telescopes. The red circles and triangles are the data observed in 24, and in black we have the data in 2012. As you can see here, the fluxes of this line, which is a really nice tracer of X-rays, has changed. So we estimate, using this data, we estimate that as the flux has decreased in 60%, which is a lot.
Yeah.
It's a considerable. So it's actually this is consistent with what was claimed before by other people. So it's this part is showing that we are observing actually variability in X-rays in this region.
Yep. Yep.
So we move if we move to the next figure, probably you are asking how you know how we can estimate the effects of UV photons in our positions in our regions. Here I is showing a sample of spectra, X-ray spectra.
Yes.
Here in the X, yes, for four positions, for position 1, 3, 9, and 12.
Yes.
In the X-axis, we have energy, and in the Y-axis, we have the counts. Yes. The black and red lines show our best fits to the data that we use to derive the fluxes of the iron line, and also to derive the flux, or to estimate the continuum at these energies. So it's just a sample. And if please go down to the next figure.
Okay.
So as I was saying, what we use to estimate the effects of the UV photons. So for that, we observe with the IRAM telescope radio recombination lines, which are really, really nice tracers of the effects of UV photons. Yes. Again, we have our 13 positions.
Yeah.
We have in the x-axis, we have the velocity and the intensity in the y-axis. So we have, as you can see in this figure, yes, in position 1 and 2, the lines, the radio recombination line shows the highest intensity in our sample. Yes. So actually the intensity of the line one divide by 9. It's just to have a better visualization.
Ah, got it. Got
So,
it.
yes. So we use these lines to estimate the electron density. So we have using the intensity, and using a equation that is known, really good known. We estimate the column density, the electron density, and we found that the highest electron density is found in position 1 and 2. So we classify these regions as dense ionized regions, and also using these lines, we classify regions 3, 5, 7, 8, and 9 as regions where we have diffuse ionized gas.
Okay.
As we can see here in this figure, in positions 10, 11, we don't detect.
Yeah.
So actually we were in the right path. So these regions can be considered as quiescent regions. So we don't have here over there we don't have the UV photons. Actually we don't have effects of UV photons. Okay. So we use this part to study the UV effects in these regions and to classify. So if we move to the next figure.
Ooh, nice big table. Okay, please say.
Okay.
See if I can blow that up a little.
Yes, over there. Okay.
We'll go here.
Okay. What we have there, here we just show again our positions. We have there the line. We have each C plus lines that we use in our study. On the top, we have the transition 1 to 0, and below we have the transition 3 to 2.
Yes.
So we have, for example, in position 3, we have the black histograms show our data, and the red lines show our best fits.
Yeah, okay.
We have our best fits. In some cases, we have the 2 lines, or our fit is better. In some cases, we don't detect the 3 to 2 line, so no, our fits are worse.
Right.
Okay, we feed these lines and the lines of this molecule and the other molecules that we were interested in using a software which is Matkuba, but assuming LTE conditions, okay, local thermodynamic equilibrium conditions. Yeah. So that is an important thing that we have to take into account, consider. And the aim of this was to derive several parameters of the lines, and at the end, what we have after fitting these lines, we have the column densities of this molecule and the excitation temperature of the molecule. So that we have at the end after the fitting. So what we did the same thing for the other molecules. I mean, for each CO, if we move down, we will have another figure where we show our fits of the each CO lines.
Ooh, nice. Okay.
I think that is the next figure where we have our spectra and our, yes, that is, again, we have in this case, we have in the X axis, we have the frequency, and in the Y axis, we have the intensity for our 15 positions. We have in black lines or data, and the red lines showing our best fits.
Okay.
In, for example, in position 4, position 3, I am showing other features that we have, yes, because in some positions we have are regions that are actually really rich. We have a lot of molecules there. So for this reason, I am showing other features, how like methanol lines. We have each 15 CO plus. Also, we have silicon oxide over there and other molecules. So as I said, the red lines show our best fits for deriving the column density and the excitation temperature. So if we move.
Hold on one question. So UN here is an unknown line feature?
Yes.
Okay.
Yes. That is right. Actually, what I use, we have different catalogs. Yes, for example, the GPL catalog, okay, which was developed in the United States, but I also use catalogs where we have the spectroscopic information to identify these lines. For example, I use another catalog which was developed in Bonn, in Germany, the CDMS catalog, but using both catalogs, I mean the information that we have in both catalogs, I was not able to identify those lines. So for this reason, I write unidentify lines.
Okay, good, thanks. Okay, yeah. We go to figure 8.
Yes, please.
You got it.
Okay, over there we have or spectra of CO plus, the other molecule that we were interested in.
Okay.
That was actually a challenge because we have a complex scenario there, because we have, especially in positions 1 and 2, we have the emission contribution from other molecules. So in position 1 and 2, we have the contribution from methanol. Yes, the lines are shown with these red lines.
Yep.
Yeah, the lines are showing the frequency or the velocity where the line peaks are expected. So for this reason, because it's very complex, we feed the lines at the same time. I mean, we feed the methanol and the CO lines at the same time. I mean, simultaneously we feed. So this way we were able to know how much is the contribution from other molecules. So this way we were able to derive the column density of CO plus. Here we can see again one important thing that I would like to stress was that in position 9, we were able to estimate, yes, really good, to fit the line and also to derive the column density. Yeah. Why? Because in this position, we didn't have a contribution, an important contribution from methanol. So that for this reason, our estimations are better for these positions. So that was nice. So if we move
Right.
to the next figure, we have a really nice lines of CO that, as I said, were used to estimate at the end the abundances. Have different lines for or 13 positions. In some positions, as you can see here, we have different components. It's because in Sagittarius B2, we have different components moving along the line of sight. For example, in position 8, we have 2 components. In position 9, 2 components as well.
Yep.
Yes, the lines are showing, the dashed lines are showing the velocity of the lines. And in positions 7 and 15, we have more components. In position 7, we have 3, and in position 15, we have four components.
Yeah.
So it was a little. Okay. If we move down, please. So we, again, the red, in this figure, the red lines show our best fits that we use to estimate the column density of CO.
Right.
Then we move to the discussion. What I think is the more interesting part of the paper.
Well, and here, let me check some. So these are your 13. These are your column densities. H2 totals.
Yes.
V is about 100 suborders. Okay. That's a nice figure.
Yes. Okay, in the next, here, please. Here, I just I am showing, we have again in the X axis, we have the positions or 13 positions, and in the Y axis, we have the abundances. So we have the abundances for our four molecules. I mean, each OC plus, each CO, CO plus, and each CO plus. So we can see here that each CO plus is the molecule that shows the highest abundances, while in the other hand, the each OC plus molecule shows the lowest abundances in our sample. But what is more interesting in this figure is that, again, in this figure, what we have is we have classified that we know in advance that are regions affected by UV photons, like positions 1 and 2.
Yes.
And we have also regions where the gas is quiescent. For example, positions 11, 12, 13. What is really interesting there is that, for example, for each OC plus, we have high abundances of this molecule in position 1 and 2, but also in regions where the gas is expected to be quiescent. So if the question is, if we think, if we know that these molecules are thought to be tracer UV photons of regions affected by UV photons or X-rays, why we detect or we have high abundances of each OC plus in these regions? So we can think, we can discuss a little bit about the chemistry of this molecule. So for this reason below, we show outputs of chemical models that we run to try to investigate the chemistry of these molecules or in more detail. Yes, over there. Yes. Here we have with different lines the outputs of the Nautilus Code. Is a chemical code that we use to simulate the chemistry, how the chemistry of our target molecules change with time. So in the axis we have time in years, and in the Y axis we have on the top panels we have the abundance, and in the bottom panels we have ratios. Different, we have ratios over there. Yes. Okay. So we have different lines with different colors because we use 4 values for the cosmic rays ionization rate. We have 4 different values. Okay. So we want to see how they change with time. So that was the reason for that, to use 4 different values. So, and also we have 2 different temperatures. We have a temperature of 50, 100 Kelvin. Why? Because we know in advance from the literature that these temperatures are like lower and upper limit for the temperatures that we have in Sagittarius B2. So these were the conditions that we include in the code and then let it run. So the output is there. The continuum line in show we have for 50 Kelvin, and in without left the output for 100 temperature. So what we can see there is, for example, for each OC plus, that when we move from low to high cosmic ray ionization rate,
Yep.
yes, the abundance change. So when we have a higher rate, the abundance is higher. When we have the low rate in 10 to the minus 17, we have the abundance is lower.
Okay.
Yes.
Okay, solid line was for 50 and dotted was for 100. Okay,
Yes, yes.
got it. Okay. Mm-hmm.
It's like I know it's a bit a busy block. Okay, so yes, we have so we see that the abundance for each OC plus for this molecule changed with the cosmic rays.
The higher, the higher. Okay,
Yes.
I'm with you. Uh-huh.
And in these figures, what we show with bands
Yeah.
in gray, we show the values that we derive for
Mm-hmm.
these molecules, the
Yep.
values. So what next? What we check is what regions or outputs we derive this for obtained with the Nautilus Code. So as you can see here for each OC plus, we have values that are in agreement. For example, a yes in these regions
Mm-hmm.
at scale times between 10 to 3, 10 to 4 for different, yes, for different uh, rates, for different rates, but also at higher time scales. So we play a little bit with this. So but we check or we figure out that, for example, for the rate of 10 to the minus 16, which is in agreement with what was derived for Sagittarius B2, that value is, I would say that is that agrees with what was derived before the studies. We our analysis focus more in this value further. So we focus more in value.
Okay.
We can see that in this case, for example, we will say that each OC plus could be explained with can be explained with 10 scales here, 10 to the 5. In addition, we using this figure, we will say that what we have in this in the code, we simulate actually two things, especially two things. We have in the code the effects, the chemistry of high temperature chemistry, and in addition, we have the chemistry of cosmic rays. Those are the main ingredients that we have there. So
Okay.
you see, comparing this and taking into account this comparison, we can say that somehow high temperature chemistry and cosmic ray can explain the abundances that we are observing in Sagittarius B2.
Okay.
But that doesn't happen when we compare or the values that we derive for each CO and CO plus
Right.
what we have over there, because there is not a really nice agreement between the output and values that we derive. We have a difference, important of orders of magnitude. So each reason we think that other mechanisms are involved in the production of this molecule. For example, shocks could be an addition mechanism that is needed.
Okay.
And as you can see for CO plus, we have a really big difference
Yeah.
between what the code shows and what we derive. We have a really big difference.
Bias.
So
Yeah.
based on that, we also, yes, we also in the paper that CO plus probably is only expected in regions where the effects of UV photons are really, really important. We were not able to include the effects or the UV photon chemistry in code. So we think that CO plus is expected only in regions that are strongly affected by UV photon. For this reason, we don't have a match there between what the code shows and what we derive.
Okay.
So that was a nice result. And in the bottom panels, we just compare what the code shows for these ratios, which are these ratios actually, I mean, each CO plus over each OC plus, each CO plus over each CO, and the other ratio are also considered good tracers of the effects of UV photons and X-rays. We also compare. Mhm.
Yeah. Okay. Uh-huh.
Yes. And I would say if we move to the next figure, I can tell a little bit about another important result. I will say the most important. We found a really nice relation between the mechanism that is heating the gas and the ratio that we derived.
Mm-hmm.
So we were able, okay, that one. Yes. Here we have in the x-axis, we have different parameters. We have in the first column, we have the H2 column density.
Yep.
Then in the middle, we have the electron density. And on the right, we have the fluxes of the iron line in the x-axis.
Mm-hmm.
On the y-axis, we have the each CO plus, each CO ratio, and each CO plus, each OC plus ratio. Yes. As we can see, we have a really nice correlation in the first and in the second columns. We have, yes, with different colors, we have classify, or we have we are showing the regions that are heating mechanism. In red, we have the regions that are dense ionized regions.
Uh-huh.
Yes.
Yes.
In black, we have regions regions that are ionized region. In blue, we have the regions that are quiescent. So as you can see, the lowest values are for regions that are dense H2 regions, and the highest ratios are for regions that are quiescent. So we have
Yeah.
a really nice correlation over there. But on the other hand, in the third column, we see that there is not a correlation between the line iron and the ratios. There is not a correlation. Of course, we have different limits, upper limits over there, which are
Right.
shown with arrows.
Uh-huh.
Yes, with arrows
Uh-huh.
are our upper limits. So that was a really nice result. But the most, another important aspect was that each CO plus over each CO is a better tracer because it shows different values for the three types of sources that we have. But each CO plus over each OC plus shows values that are similar for regions that are diffuse and regions that are quiescent. So we have more or less the same regions. So we were not able to separate these different sources. So for this reason, we claim in the paper that each CO plus over each CO ratio is a better ratio because it's really sensitive to the heating mechanism.
Yeah. Mm-hmm. Yep. Separates nicely there. Uh-huh.
Yes.
Very cool. Nice. Do we got one more? Is that it? That's it?
Yes. At the end, we in the next page, I guess we have the conclusions. What I have mentioned.
Uh-huh. Very nice. Very good. Yep. This is the money plot. Okay.
Mhm.
Um,
Yes.
So Hiro, let me ask you, where do we go from here, given what you've published? Do you have more observations in the pipe that you've already taken and you're just waiting to reduce them? Are there more than 13 target areas that one could go after? Sort of where does the community go over the next 5 years to move this topic along?
Oh, actually, there are many works that people are doing in this field, especially using interferometers like ALMA, like the ones that you have in the United States, like the BLA,
Mhm.
array. So people are using these telescopes to study the nuclei of other galaxies. Here I show what we study in the Milky Way, the closest nucleus that we have, and people are using to study the nuclei of other galaxies using because we have using interferometers, we have a much better spatial resolution. Is these instruments are more sensitive. They have better spectral resolution. Are more sensitive, so we are able to detect lines that are not so lines that don't have high intensities. So the people are using in our community are using these interferometers. Um, I was very happy because this last year in July, I think, we observed, yes, remotely with the IRAM telescope again. But in this case, we observe the regions, not just positions, we observe regions. So what we want is to study the thing, to do a follow paper, but showing already maps, showing how the effects of UV photons are, but considering the extension in these regions in this globe, I mean in Sagittarius B2. And also I have data also that we observe with the IRAM telescope to study another cloud in the galactic center. But in this case is Sagittarius C. We have a lot of Sagittarius, Sagittarius A,
Yes, quite a
Sagittarius
few.
B2.
Yes, lots of Sagittarius is in there. Yep.
Yes, we got another follow-up paper, but in Sagittarius C. That is a really nice source also in the galactic center.
Cool. Cool. Very good. Jairo, I want to thank you so much for spending some time today and talking about your really lovely APJ article. So thank you.
Thank you. Thank you for having me.
My pleasure. My pleasure. All right, everyone. Thank you so much. And we will see you on the next one. Bye-bye.